Welcome back. In the previous classes, I was discussing about proportional control, proportional and integral control, and what we have observed that in presence of vanishing and non-vanishing disturbances, both control are not efficient in several cases. In today's lecture, I am going to explore the most commonly applicable control, that is PID control. So, I am going to incorporate the information of the future, and after that we are trying to understand the tuning process and going to explore that PID controller is able to compensate uncertainty or disturbances or not. If not, then what is the future possibilities. So, this is the purpose of the discussion. So, we are trying to understand the tuning process of proportional derivative control, proportional integral derivative controllers, and I am going to use exactly same framework. I am also going to take the example of the first order system. So, in previous class I have taken example of the underwater vehicle. So, same example I am going to continue in this lecture also. We are also trying to analyze the limitation of the output feedback. So, suppose that if I have second order system and if I have just information of the position, means x1 dot equal to x2, x2 dot equal to u plus dt, I am assuming. So, x1 we are interpreting as a position vector. So, if I have information of position, so is it possible to stabilize the second order system at the equilibrium point? Our answer is negative in this case. So, we are going to explore the PD controller, and it is possible to show that using PD controller one can able to achieve this objective. Last part of this lecture is based on the high gain feedback, and it is possible to show that high gain feedback is closely related to the sliding mode control, which is the topic of this particular course. So, what kind of outcomes we are expecting from this particular lecture? We are trying to understand the tuning process, and we are also able to understand the connection between high gain feedback and sliding mode control. So, let us start the today's lecture. You can see in today's lecture, again I am going to start from the very simple example. So, I have taken the mathematical model of the underwater vehicle moving in one direction, and if you have we have seen the first class, at that time we have done mathematical modeling like this. So, this is the thruster force, this is the drag force, and after that we have the disturbance, and after that what we have done, we have designed this as a feed forward action. So, this is drag force. So, I am going to compensate the drag force, and after that we are going to design the feedback. So, here E is nothing but our objective to stop underwater vehicle. So, V minus 0, and due to that reason E is exactly equal to V, and now I am going to design this particular feedback. So, in today's lecture I am going to involve the information of derivative also. What is meaning of derivative? We are trying to use the futuristic information during the design process. That is our goal. Now, you can see here that our closed loop system, right hand side of this differential equation, is also containing the information of the derivative. So, due to that reason I am going to rearrange this term, and finally our closed loop system, you can see that that is exactly like the proportional action, and here we have some kind of disturbance. and this disturbance dt may be non-zero or constant or time varying. It is possible to show that again Vt is uniformly bonded or uniformly ultimate bondedness kind of result comes into picture. So, I suggest that what you can do, you can again go to the second lecture where we have discussed the proportional control and then try to calculate this bond in the case of the disturbance. You can able to see that ultimate bond is a smaller because this disturbance is scaled out by the 1 plus Kd where Kd is positive. So, what is our observation? In presence of the proportional and derivative controller, again we can not able to completely reject the disturbance, but we will get some kind of ultimate bond or uniform ultimate bond. So, that is the our observation. It means that PD controller is also not insensitive with respect to the constant disturbance or time varying disturbance. So, let us try to see the advantage of PD controller in some other case. Okay. So, what basically we are going to do now? So far we have just discussed the how to control the velocity. Now, suppose in the same mathematical model, so mathematical model is V plus U and plus dt. I am assuming that there is no disturbance for time being. So, mathematical model is just V dot equal to U. Now, using this mathematical model, I am trying to control the position. So, I have to involve the position. So, I am assuming that x1 is the position. So, x1 dot equal to x2, x2 is the velocity and x2 dot equal to u. So, this kind of mathematical model comes into picture if I am trying to stabilize the position as well as the velocity, then first order mathematical model is converted into second order. Now, suppose that if I have just information of the position, so x1 is the position vector, so and after that I am going to scale it up and after that I am going to utilize this as a feedback. So, you can see the closed loop system, that is second order system. So, now whenever I have second order system, so directly I cannot able to apply the philosophy of Newton. What is our philosophy? Philosophy is very simple. If something belongs to the real line, so you can just see that quantity and their rate of change of quantity. If that is in opposite direction, then always we can able to observe the motion, that is the direction of the velocity. So, here V is positive, V dot is negative. If you are here, then V is negative but V dot is positive. So, we will see this kind of motion. But now here we have second order system. So, in order to apply Newton's philosophy, I have to decouple the second order system, and it is possible to show that there are several other coordinate frame exist where these two states x1 and x2 are decoupled. So, now how to decouple? So, one of the simplest way, you can transform the system in the polar coordinate, and due to that reason I have defined like this: r is positive and that is given by square root k x1. So, due to that reason k x1 square plus x2 square. Now, what you can do? Again you can calculate the rate of change of this r, that is radius. It means that in second order system object is represented by radius as well as angle this theta. So, now I am going to see that how basically radius is changing, how angle is changing. So, you can see that after calculation or r dot if I calculate and after substituting this closed loop system, I will get r dot equal to 0. What does it mean? It means that r is nothing but some kind of constant quantity. It means that once x1 0 and x2 0, that is the initial condition is fixed, then value of r is fixed and that is not going to change. Okay. Now, let us try to see the behavior of the theta. So, again I am going to do exactly same treatment. So I have calculated theta dot and going to substitute this value from the closed loop system. Here I have used one more inequality, equality, that is sec square theta is 1 plus tan square theta. So sec square theta is 1 plus tan square theta, and due to that reason we have x2 square by k x1 square. And if you rearrange the term, then finally you will get like this. It means that now you can see that k is some kind of gain. So rate of change of theta is also constant. What does it mean? Theta is actually decreasing with respect to time because I have negative value. Okay. Suppose that initial condition of theta 0 is 0, then what happens? What kind of observation we will get? R is constant, and then I have this kind of motion, and due to that reason I have some kind of harmonic motion, but I cannot able to move to the equilibrium point. So what kind of conclusion we have seen from this mathematical treatment? That if I have just information of the position, even if system is free from the disturbance, I cannot able to stabilize the position and velocity. Let us try to take another example. Suppose that if I have information of the velocity, so what kind of conclusion I can actually draw in this case? Let us try to see that if I substitute u equal to minus k into x2, then at that time x1 dot equal to x2 and x2 dot equal to minus k into x2. You can see that this is already decoupled equation. So x2 is tending towards 0 as t tending towards infinity because k is positive. So you can just apply the Newton's law, and what kind of observation you will get? That x2 is tending towards the 0. It means that x1 is constant. It means that using just velocity information also I cannot able to stabilize the system at the equilibrium point, and due to that reason I need both information. So how to get another information? Suppose that if you have just information of position, then you can design one differentiator, and then you can differentiate this signal and get x2 information. Another way, you can design some kind of observer, but most of time whenever you are observing some signal or measuring some kind of signal with sensors, then they have always noise, and if you are going to differentiate that noise, and if noise is high frequency, what is meaning of high frequency noise? Suppose noise is represented by some kind of sinusoidal wave, and omega is very high, alpha is very small, but after differentiation what happens? That I get alpha omega 0 cos omega t, and this omega, this is very high frequency noise, so that is going to amplify during the differentiation process, and due to that reason implementation of PD controller has still some kind of challenge. So we are going to see that how to mitigate this challenge in the subsequent lectures. So here I am assuming that our differentiator is robust and exact. What does it mean? That we can able to differentiate signal in presence of noise also. Now if you design control like this, so at that time now our system is basically looks like something. Here I have k1 and minus k2, and here I have x1 and x2. So again this is second order system, so you can apply the transformation same like the previous class, decouple the system and apply the Newton's law. And what kind of result we have actually observed in the previous class? That if eigenvalue are strictly negative, then both quantity x1 and x2 tending towards the 0. Okay, and in this way I can able to design the PD controller. And what is our observation? Both x1 and x2 is tending towards 0 as t tending towards infinity. It means that we can able to solve a stabilization problem using PD controller. So every control has its own limitations, own benefit. So you have to understand each and every controller. Whenever you have some kind of physical system, so you have to go through proportional control, proportional integral control, PID controller, and try to see that what kind of advantage we will get, and then you can select the final control for your practical implementation. It is good to simulate this system, and here this is exactly looks like the PD controller, but what kind of extra information here we are doing? We have using the signum x1, and you can see that this is the scaled value of the present information and future information. It is possible to show that both x1 and x2 equal to 0 in finite time if there is no disturbance. Okay, so this kind of simulation please do by yourself. Now let us try to see the treatment of proportional integral derivative control using same framework. Here I am assuming initially d not equal to 0 and that is constant, but you can easily able to generalize. You can take dt as a some kind of time varying signal. Now here you can see that I have used the information of present, past and future, and then I am going to apply to the same first order plant, and after rearranging, after absorbing this dot term in the left hand side of differential equation, I will get this equation. Okay, so you can see that again this is exactly looks like proportional integral controller with a scaled value of the disturbance. So again what you can do? You can treat this as a extra state, take the derivative, apply the transformation and design the gain. So if dt is constant, so now again you can able to see that PID controller is insensitive with respect to disturbance, but dt is time varying, then again you will get the uniform bond or ultimate bond similar like the proportional integral control. So now I hope that you are able to understand the classical proportional control, proportional integral control, proportional integral derivative control. So whenever you will see the subsequent lecture, we will come up with this some new form of the PID controller, that is called non-smooth PID controller. So before coming there, what I am suggesting you that you can simulate. Okay, simulation will give you lot of idea, and here how to define this phi. So this is the definition, you can apply this definition, y you can replace by this value, and please do the MATLAB simulation, and you can able to observe that again x1 and x2 both equal to 0. If dt is some kind of differentiable uncertainty or noise, then x1 and x2 tending towards 0 as t tending towards the infinity. You can also simulate this, and same kind of observation you can able to get here. Why I have actually keeping this kind of slide? Because you are able to understand that sliding mode control is not different from the PID controller. Just here we are using the scaled information of present, past and future. Okay, so you can see here this is the present information, this is the futuristic information, and this is the past information. Now let us come to the some new kind of controller, that is called high gain feedback. So in the starting class I have told you that most of time in this network era people are believing on the present information. So is it possible to mitigate all different kind of uncertainty if uncertainty is bounded with help of the present information or not? And somehow this controller, that is called high gain feedback controller, is giving a room. Using that it is possible to show that you can able to nullify any kind of disturbance, either that is vanishing, non-vanishing, constant or time varying, any kind of disturbance you can able to reject using high gain. But we have limitation in terms of the actuator, because every control we are actually applying through the actuator, and every actuator has some kind of finite bandwidth. Okay, so particularly nowadays we have lot of electrical actuators where DC motors we are using, or some kind of motors you are using, and we already know that they have finite bandwidth. So implementation of this control is challenging in that case. But suppose if you have pneumatic actuator, hydraulic actuator, you can able to apply this kind of control. So what is philosophy? Philosophy, you can see here that again I have proportional lag control and I am scaling it by 1 by tau, where tau tending towards 0. And if you substitute this control, so after substitution, what kind of things I will get? So after substitution, you can see here that I have equation like this, and since tau tending towards 0, so I can expect that in presence of any class of disturbance, you can substitute here D as a some kind of constant, time varying, or any class of disturbance, one can able to maintain V equal to 0. Okay. So mathematically it is possible to reject any kind of disturbance with help of the high gain feedback. Why term high gain? Because you can see that as tau tending towards 0, gain is tending towards the infinity. So I am going to do the MATLAB simulation. So during MATLAB simulation, slowly I am decreasing the value of the tau, and you can see that our response, I have started from here and they are tending towards the 0. If I increase the decrease the tau by very small amount, then exact compensation we can able to see in presence of the sinusoidal noise. So what is discussion? Discussion point here that high gain feedback is able to compensate any kind of disturbance. You can see that order of the system is reduced by 1. So we are going to see that why I am writing this particular statement. It is become more clear if I take the second order system, and control has infinite magnitude. Why? Because tau tending towards 0, then value of control is tending towards very high value. So let us try to see what kind of observation we will get if I apply high gain feedback to second order system. So I have taken second order system and I have assumed here that any kind of disturbance, either vanishing, non-vanishing, or time varying. So this D is containing all possibility of the disturbances or uncertainty. Again I have designed some kind of proportional derivative kind of control, and then I am scaling it by 1 by tau. So why I am telling this as a present information? Because second order system, so I have used two different sensors to estimate x1 and x2, or measure x1 and x2, and then I am going to design the control like this. So again this is high gain feedback controller. Here I am assuming that tau is very small. So if you already assume tau is very small, so there is no need to write limit tau tending towards 0. So closed loop system is given like this. Again you can multiply both side by tau, and then you can able to see that we will get this kind of relation. Okay, so I have defined Z in another way. You can define Z as a this term. So this whole term you can divide as a Z. You can transform in the Z coordinate frame, and then you can maintain tau very small. Then you can see that I get this kind of algebraic relation between x1 and x2, both state x1 and x2, and due to that reason x1 can express in terms of the x2, and after substitution of x2 in place of x1 dot equal to x2, I will get this kind of differential equation. And since Kp and Kd both are the positive, so you can apply the Newton's law. Again, if you are here, then x1 is positive but x1 dot is negative, so we will move in this direction. Okay, if you solve it, then you will get this kind of response. So this is nothing but the exponential convergence. So as t tending towards the infinity, x1 is tending towards 0, and x1 and x2 both are coupled, and due to that reason x2 is also tending towards 0. So what is our interpretation? So we have extremely fast convergence because tau is very small, so 1 by tau is very large. Okay, and due to that reason in a just few moment you are able to get this kind of algebraic equation. So overall system is reduced by x1 dot equal to x2 and this equation. So this is differential algebraic system, and then I will get convergence of x1 and x2 in presence of any class of the disturbance. Okay, and this is exactly the same idea of the sliding mode control. So, in sliding mode control we are designing, suppose that if I have second order system, so this is the equation of the Kp x1 and Kd x2 in the two dimensional plane. So, using control we will converge here and after that we will slide here. Okay, and due to that reason there are close connection between high gain feedback and sliding mode control. After that precision is also high because this is able to mitigate any kind of disturbance. Only issue is the unbounded control. So, this will give us the next homework, that is it possible to design some kind of control which has finite gain and we are able to achieve same kind of behavior. Answer of this question is yes. Using sliding mode control we can able to do. It means that value of the control gain remains the finite and we can able to compensate any kind of uncertainty, any kind of bounded uncertainty if that will enter through the control channel, provided our actuator is strong enough. So, what is conclusion of this lecture? That we have explored the proportional derivative, proportional integral derivative control. We have understood the limitations of the output feedback. We are able to understand the connection between sliding mode control and high gain feedback, and what is our future direction, study the impact of actuator limitations on high gain feedback, because still whenever people are using hydraulic or pneumatic actuator, they are utilizing this kind of concept. So, if you have actuator like hydraulic or pneumatic, it is good to explore the high gain feedback control. So, with this remark I am going to end the today's lecture. Thank you very much.